All right, welcome back to the PyCSE channel. Today I wanted to do something a little bit different than I've been doing. I've spent quite a bit of time focusing on some of the core features in Python and NumPy and SciPy and things like that. Today I want to talk about estimating uncertainties in Python. And this is a really common task in science and engineering computations. The example I have in this little cartoon here is, say we've measured a mass of 1.1 grams and we know it's plus or minus 0.2, and the volume is 0.7 centimeters cubed plus or minus 0.05. And the question is, what's the density? And of course that's just the mass over volume, so 1.1 divided by 0.7. But what do we do about those uncertainties? How do we propagate those and figure out what the uncertainty in the corresponding density is? And so the conventional way of doing this would be to use a lot of these rules. There's a rule for every kind of operation. So if I know that A has some uncertainty and I multiply it by a well-known number, then the uncertainty in that product is given by sigma squared f, and we just multiply a squared times sigma a squared, and we can estimate it. And here we have rules for when you multiply and add, or when you subtract, or multiply, divide, raising to the powers, logs, and so forth. And so there are just one of these rules for every single kind of operation you could want. And as you get more and more complex, you have to combine these in different ways. So if you add things and then divide things, you have to kind of propagate the rules one at a time, and it's pretty tedious. Now, all of these are really special cases of the rule up here, which is the basic idea is you take your function, expand it in terms of the parameters with unknowns, and then the variance, the sigma f squared, is just the partial derivatives squared times the uncertainty squared for each one. And this is certainly doable. You just have to work out what the derivatives are for every single parameter, and then apply this. So what I've learned about is a package called uncertainties, and uncertainties makes this all pretty easy. So if we go back here, this is the uncertainties package in Python. What you do is import a ufloat object, and then you can use instances of that to do algebra of this sort. So let's take a look at some examples. Let me pick one here. Let's say we have, let's just do an easy one here. Let's do a minus b, where we have some uncertainty on a and some uncertainty on b. We'll assume no covariance for now, so this term will be 0. And then the sigma f is just the square root of these things. All right, so what we do is import the uncertainties. I usually do it as a namespace here. And let's make two variables. So we're going to say u.ufloat and say that it is a nominal value of 2, and say an uncertainty of 0.2, and b will have a nominal value of let's say 3, and 0.03 as the uncertainty. And if we just add these two together, a plus b, then what comes out is 5 plus or minus 0.20223. And the let me import np here. The rule should be something like np.square root of 0.2 squared plus 0.03 squared is the variance in the sum. And that's what you see here, right? This quantity is right here, and it's the same as what is automatically calculated by ufloat. So regular algebra works really great, and all the a plus b minus b divided by v times b raised to the power, all those normal algebraic operators work perfectly fine. And so we can even do something like a raised to the b, and that tells us that it's 8 plus or minus 2.4. And does that make sense? Let's see, here we had, is there one that has that? A to the b, down here is a to the b. So we have this like complicated formula that you would have to work out what these are, and it's really just this term and this term, and I'll leave that as an exercise to do that. Okay, so the regular algebra is super nice. We can already go back up here and answer this question. So let's do it here. So we have u dot u float. Let's see, we had 1.1 plus or minus 0.2. 1.1 plus or minus 0.2. And then we're going to divide that by another u dot u float. That is the volume 0.7 plus or minus 0.05. And we get right away the density 1.57 plus or minus 0.3, and it's pretty convenient. We can even say something like, let's do it like this. Note what happens when we print row. So here we're getting the display, but when we print it, it actually uses some judgment on what the significant figures are automatically, and we can even embed this in an F string. So if you know you want, say, 1.3F, I think this will work. Then we can see even with nice fancy formatting. All right. The way this program works is that uncertainties knows about the derivatives of many of the common operators and many common functions. Not all of them, but many of them. And so to make sure that you get the right support for other functions, you have to look at this uncertainties.umath. And these are functions that are known inside uncertainties to work. And let's try a couple of them. Let me see, np dot, let's do exp of u dot u float 2, 0.5. All right, so out of the box, this results in an error because we're using the NumPy exp and not the version that comes with uncertainties. That's one practical limitation of uncertainties, is that what we need to do is say from uncertainties.umath, let's just import everything so that we have it. And then instead of np, we just do exp. And then we get the correct propagated uncertainty. And anything that's not in here is likely to cause a problem. And like you just saw, if I try with np.exp, then we see we got an error. But this is often extendable. So here, if I write u.wrap np.exp like this, let's see if that works. Then we get the same answer. So there is this u.wrap function. It's actually a decorator. And so here we're decorating the np.exp function, and then it's able to manage getting u.float out of this. There's some magic that happens there, and I'll show you more magic in a second that makes me wonder how this works to just wrap it. Because if we look at the wrap function, or this decorator, then it wraps a function to accept numbers with uncertainties. So the wrapped function returns the value of f with correct uncertainty and correlations, and it allows you to wrap things that might be written in Fortran or C or something like that. So your function has to return a float-like thing, a float or an integer. It does not work on an array apparently, and there's a couple of other requirements. And this is the one that I find like really remarkable, that we're not telling it anything about the derivatives of np.exp, but it's somehow getting them and doing the right thing. And we'll know that it's doing the right thing here in the next example. So similarly, let's say you want to use the error function in SciPy. This is not a supported out-of-the-box function, and so we have to wrap it like this. And so this is an alternative way of what I did above. We use uncertainties.wrap on the error function. And now when we run this, we get an answer. And it's a good question of like, is that the right answer? And how do we know? So I'll show you briefly that there is a way for us to use Monte Carlo sampling to demonstrate what we're looking at. So let's go back up here, and what I have here is that x has the value 0 with some uncertainty, plus or minus 0.01. So if we want to evaluate what is the error function at 0 when it has some uncertainty in it, one way we could do that is draw random samples from the normal or Gaussian distribution. And so here I have a random normal distribution that has an average of 0 with a spread of 0.1, and we make 50,000 samples of it. And then I can calculate the error function of all 50,000 samples. So now y is an array of 50,000 entries evaluated on the error function of x, where x is now this normal distribution around 0. And we can calculate what the average of that is and what the corresponding standard deviation is. So if we do that, then we get an average that is about 0. It's not perfectly 0, but it's about 0. And here we get a standard deviation that is like 0.112, and that's very close to this up here. Now this derivative up here is exactly the derivative of the error function evaluated at 0 times maybe with this uncertainty level in here. So it's exactly the partial derivative of the error function with respect to x times the uncertainty in here. And so this is exactly the right answer, and we can use this statistical analysis to show that we get something that's pretty close. Now, some interesting things happen when you get too broad a variation with this particular function, and I want to show you what happens just because, one, I don't totally understand it, and two, it's interesting how it seems to break down. So let's come back up here and take our x, and let's say that now our standard deviation is plus or minus 1. When I run this, you get 0 plus or minus 1.128. And again, you'll have to take my word for it. I looked it up. This is exactly correct for the derivative of the error function times this sigma f. And so this is a mathematically correct uncertainty as far as I can tell. But let's see what happens when we try to do this Monte Carlo simulation. If I run this, we only get an uncertainty of about 0.68. And it doesn't matter how many steps that I put in here. Something's up. And the thing that's up is we have to look at the histogram of the corresponding results. So if you look at this histogram, this is not a normal looking distribution. And you have lots of concentrations at -1 and lots of concentrations at 1. And so this 0.68 is the standard deviation of this particular distribution, but it doesn't represent a normal distribution. And so I think the Monte Carlo solution is failing here because of that. So when we take the mean and the standard deviation, we're kind of assuming the distribution we're looking at is a Gaussian looking distribution, and this one isn't. And why is that? Well, maybe we can plot what the function actually looks like, and we'll see kind of what's happening. I think we could try this. Is that going to be, this might be a hot mess. Let's change this to just dots. All right, so this is what the error function looks like. And so once you get, plus or minus out to 2, this plateaus at a constant here and at a constant here. And so when we turn this into this histogram, that's why we're seeing this large peaks here and here. That's messing it up. All right. So there's a couple of other wrinkles that are worth noting. I think as you start using uncertainties, I would rely on it primarily for algebra, regular old algebra. And then if you need it to work for some other functions, there are the functions that are built in and available in the UMath library. Where's that? Up here. So these are many of the standard functions that you would want to use. And then if you need to go further, it can be a little bit tricky. to work out. So let me show you one example of how to do this with fsolve. So suppose you have this function a times the error function of x, and we want to say when is that function equal to 1. The normal way to do this is you write a function that will be equal to 0, and a is a parameter here. I'll tell you why in a minute. And then we just run fsolve, and it finds a value of x that makes this equal to 0. And out of the box, this does not work with uncertainties unless you follow the little tricky recipe that I've worked out here. And I had a little help from the author of Uncertainties many years ago to work this out. But we'll work out and kind of explain how it goes. So what we do is define a. A is the thing with uncertainty here. And we have an initial guess that we don't know. We have to define a second function that we're going to run fsolve in. And that function has the initial guess and the parameter a as an argument. And that inside there we do the fsolve. And so here we're passing a as an extra argument to our function, and then we're returning the solution, which has to be a float. That's why we have a comma here that unpacks the one-dimensional array into a number. And then we just wrap that function so that uncertainties can be propagated the right way. And when we run this, we get a number that is a solution that looks like this. So the answer is 0.476 something something plus or minus 0.03. Right? So that's how certain we are of where the true value of x is, given that there's a little bit of uncertainty in what the a value is. Right? And if we plug this into the solution, then we could see, or into our regular function, then this would look like f. I'll just copy this whole number and pass that parameter. So this number should be something that's very close to 0. And it is, 10 to the minus 15 plus or minus like a tiny little number. So this is what the range of 0 actually comes out to be. But we should ask again, how do we know this is right? Because we put a lot of faith in the wrapper here to do the right thing. And we can try to do this in a Monte Carlo way as well. So here again, I take the idea that we make a sample of the normal distribution, in this case with a nominal value of 2, standard deviation of 0.1. Here we make 100,000 samples. You need to use enough samples to be sure that your answer doesn't depend on them. Maybe let's start with just 100 to see. And then we do a list comprehension that is basically going to run fsolve. So we just run fsolve for each different value of a, and each value of a is drawn from the normal distribution, so we'll see what is the solution for that particular a. And it's not exactly the same idea, but it's a simple way of doing it. So let's run this and see what we get. So up here, 4769 is the answer, 0.027 is the uncertainty. That's, even with 100 samples, already very close to what we get. And we can run 1,000. This is fast enough that it's easy to even go by 10,000. And we get something that is very, very close. Even up to 100,000, things don't seem to change so much, but it takes a little bit longer to do that. So we get very close to the same answer here, 477, 479, and uncertainty 028 if you want, and 028 down here. So the uncertainties package is much, much more convenient than this Monte Carlo approach, and it allows you to automatically propagate uncertainties in all kinds of ways that are sure to be helpful in working out what the uncertainty in a quantity you derive for an experiment or in the lab or from some analysis, etc. And you can use these uncertainties here to propagate, what is the impact on a design problem, for example. So if you know uncertainties in volumetric flow and reaction rates and concentrations, you can see what the impact of that might be on the volume of a reactor that you would calculate. All right, so that is a very brief introduction to the uncertainties package, and I hope you find it helpful and can use it in the calculations that you're doing. And maybe in another video soon we'll talk about units or quantities, and those can be combined with uncertainties so that you can do unit algebra and have uncertainty at the same time. So thanks for listening, and I'll see you